In the previous video, we saw how two-dimensional motion can be broken down into two one-dimensional motions. One happening at a constant acceleration in the vertical direction, and one happening as constant velocity motion in the horizontal direction. But we also saw the graphical representation of the two-dimensional motion across horizontal and vertical direction separately. But before we dive into the algebraic way of expressing this motion, it is important for us to discuss one important factor. Remember, all these quantities, when I say all these quantities, I mean position, velocity, and acceleration are all vector quantities, right? So, which means we have got both magnitude and direction. Unlike the one-dimensional motion, wherein we could express the direction of these vector quantities using positive and negative signs, it's not so possible with two-dimensional motion. So that's demanding of us to come up with a new way of expressing this vector quantity. So I'll show you how is that done now. So as you can see it on your screen now, the vector nature here is represented using an arrow here. What you're seeing right now is the velocity vector. So as you can see, these velocity vectors basically represent the velocities of the ball at various instants in time. So you can see it now. As I told you, this is just an example, which means uh, vectors are represented using arrows, which means all vector quantities. It need not be just velocity. Right. So this is how we represent a vector quantity using an arrow. Okay, now let's see how this arrow is helping us to represent a vector quantity completely. Okay, so now I'll have to go back to my iPad screen. Now, if you can see, this is how we represent a this is how we represent a vector quantity. As I told you, it's an arrow, and the length of the arrow represents the magnitude of the vector quantity, while the angle which the vector quantity, I mean the arrow, is making with respect to x-axis is going to represent the direction. That's all. As simple as that. Two components of vector quantity is represented using an arrow. Now, if I go back to the tracker file, so you see that these arrows are representing the velocities at various instants in time. And you can see very clearly their lengths are actually changing. If I go close to time zero, you can see the arrows to be very, very short here, right? However, towards the end, the arrows are increasing in size. And also, the angle which these arrows are making with respect to x-axis is increasing, but in the negative direction. They are becoming more and more negative. So, how do we know this? What is this telling us? So, what I am going to do is I'm going to take one instant in time from this file, and I would like to show you how to find the resultant velocity for that particular instant in time. The word resultant here means it's the sum of the velocities across the x and the y direction. If you remember, we saw this motion to be as two separate motions, one happening in the x-axis and one happening in the y-axis, right? So in order to save time, what I've done is I have taken the velocities across the x and y direction at a particular instant in time, which is at time t is equal to 0.33 seconds. This corresponds to the 75th frame. So you've got Vx to be horizontal direction to be 2.0 meter per second across x-axis, and Vy at that point to be minus 3.8 meter per second. I basically took this from the graph. Now, using these two velocities, how do I find the resultant velocity? Now, to find the resultant velocity, we'll have to actually draw a vector diagram which have to be drawn to scale. However, I'm not going to do that here. So what I'm going to do is I'm going to just take a line across x-axis to represent Vx to be 2.0 meter per second. So you can take the scale to be 1 centimeter is equal to 1 meter per second. Correct? So it's drawn across x-axis because it's x component and it is acting on it's positive. Now Vy is minus 3.8 meter per second. So which means my my line should be like this, right? So if I have to show it, this has to be 2 centimeter. This line has to be 3.8 centimeter. Now these are the two vector components of the motion. Now in order to find the resultant velocity, we basically use the Pythagoras theorem. So I complete the rectangle here, right? And then I draw the diagonal. I draw the diagonal here. The diagonal, this line, this diagonal basically represents your resultant velocity, the one which you saw on the tracker file. Now, how do I find the magnitude of the resultant velocity? Two ways to go about it. If you draw this to scale, the length of this line will give you the magnitude of the resultant velocity after using the conversion, the scaling. And the angle which it makes with respect to x-axis will give you the direction. So one technique is to use the scale method. When I say the scale method, you draw it graphically and find it out. The second method is to use Pythagoras theorem. So how do I find the resultant velocity? So you can clearly see there is a right angle triangle formed here, right? So it's either this one, this is a right angle triangle, or this one is a right angle triangle, right? So if I go for either of these, you'll realize the fact that the resultant velocity will be basically square root of 2 squared plus 3.8 squared. So that's how we find the resultant velocity algebraically. And what will be the angle? The angle will be basically using trigonometry. So trigonometry, so it will be what? Tan theta will be equal to opposite by adjacent. So you use that to find the angle. So that's how we find the resultant of two vectors using graphical method or algebraic method. Now there is one important point which you have to realize here. I'll just go back to the simulation, I mean the tracker file. Please remember, if you look at it naturally, by nature, the ball is actually going in both the dimensions simultaneously. So which means the velocity of the ball at a given instant in time is actually given by these arrows. These arrows basically represents the velocity of the ball which is happening naturally. But for the sake of solving the problem easily, or for the sake of understanding it easily, we have broken down it into horizontal and vertical motions. And then, as I just showed it to you, we can use those horizontal and vertical motions, velocities, to arrive at the resultant velocity, which is the actual velocity of the ball at that instant in time. Thank you.